Let's talk about conj, and that's the topic of creating collections from old collections with a new element added. Okay, so let's look at an example. Conj stands for conjoin, which is just a fancy way of saying that, well, we are sort of gluing one element to a collection. So I give a collection, which is a vector containing numbers 1 and 2, and I conj 3. So what do I get? Well, I get 1, 2, 3. So you see that the number 3 is added at the back after the last element of the vector. And that does make sense because, you know, if you imagine that, well, the vector is something that you can imagine as labeled boxes starting from 0, 1, 2, and if you want to add a new element, well, you just take the next available box and you put the next integer number on that. Imagine if we wanted to put the new element in the front, then we would need to rearrange the whole collection. So index 0 would become index 1, and index 2 would become index 3, and so on. Okay, so this is quite natural. You can conj an element on a empty vector as well. Okay, so this is all good. What happens if I conjoin on a list? Well, conj. Well, let's have a list with the same two elements. Oh, okay, so I want to do 1 and 2, and I want to conjoin 3. So what do we expect? Do we expect 1, 2, 3, or a list containing 1, 2, 3, or something else? Let's have a look. I evaluate it, and it's 3, 1, 2. That might be a bit surprising because you know, so the general form of conj would be something like this. Conj, let's give a collection and an item, okay, and that item will be put into that collection, or more precisely, you will get a new copy of the collection with this item added. Okay, but so that's the general form. So I could use it for list, but the behavior is different, and that's true. So conj as the new element is the most natural method for a given collection. Okay, what does it mean, most natural? As we saw, it's like vectors, they like to grow in the end, while lists, they like to grow in the front. And it's yeah, that does make sense, especially if you know how lists are implemented with linked lists. Then you know that it's like, well, just putting an element at the front is very, very cheap, very easy. And that's, if you think about how you disassemble a list, you ask for the first, then the rest, and that, well, again, that division is sort of explains that why it is natural for them. So yeah, conj is nice and universal. You can apply it to other collections, later hash maps and hash sets, but you have to keep in mind that the behavior is different. It can be different depending on the underlying collection. One thing we need to mention here for historical reasons, I mentioned cons, which is the abbreviation of construct. Okay, and cons, but see that the order of the arguments is different. First we have the new item, then we have the collection, which is a list in this case. So before, in Lisp, there was only one data structure, and that was the list. Okay. In Clojure, we have more data structures, for example, a vector. That's why just having the cons was not, we had to have a universal collection growing function. Okay, and this was, but previously for Lisp, we only had cons. We still have cons, and you can even do this with a vector. Okay, and it's like the question is that whether cons is doing the natural thing or just does the simple thing, and it turns out it just does the simple thing. Okay, cons does not respect the type of the collection. It says it's a vector, but it's like, yeah, I'm just producing a sequence, which is essentially just a list. So if in doubt, you can just use conj. Again, conj, collection, and the item, and that's a good way to grow collections.